Okay, thank you all and welcome to the afternoon session of the International Conference on Dynamical Systems, celebrating the 60th birthday of Marcelo. Before to present the next speaker, two announcements. One is remember all that this afternoon at the end, 5 o'clock, we have a reception. And the Wednesday will be added an extra talk after the last one. So the talk will be announced, but we finish a little bit later, around 1 o'clock. Okay, it's a pleasure to me introduce to Silvius Klein from Pontifical Catholic University of Rio de Janeiro, and he talked about stability of the Lyapunov exponent under random noise. Thank you.
Thank you, Carlos, for the introduction. Before I begin, firstly, I would like to thank the conference organizers for the invitation. It's a great honor to be here. My first time at IMPA, and in fact, in Brazil was in 2013. 9 years on, this place still looks a bit intimidating. So I came here for a conference, for a workshop on Lyapunov exponents. This is the first time I met Marcelo in person. We had a conversation about the topic that I would end up later working on, random linear cocycles. And at the end of this conversation, Marcelo has asked me if I had a family, and in case I had not, he suggested to me, he suggested that I consider moving to Brazil. A side note, at the time of this conversation, it was a Monday, I had not. This would change by the end of the week, and this event, together with his generous open-ended invitation, brought me 3 years later to IMPA. I was Marcelo's postdoc for a while here, and eventually to the Catholic University, where my current institution. When I arrived here, I entered in a group of young researchers formed or being formed by Marcelo. It was a great moment it was a very important moment in my career. I'm grateful for this. I immediately started interacting with them. Many of them are here. And eventually, I started collaborating with them. Moreover, my own students nowadays depend greatly on the work of Marcelo. In particular, I expected they would sleep with his book on Lyapunov exponents by the bedside. It's true, right? I hope it is. Well, so I'm grateful for these opportunities. I'm going to talk about joint works with outside from PUC-Rio and Pedro Duarte from University of Lisbon. Projects motivated in part by the question of stability of the Lyapunov exponents of quasi-periodic cocycles under random noise. A quasi-periodic linear cocycle, it's simply a linear cocycle of a torus translation. So given an ergodic translation vector or frequency on the d-dimensional torus, on the base we consider the translation induced by this translation, and on the fiber the linear transformation determined by a matrix valued function on the torus. For convenience, we consider this matrix is invertible with determinant 1. So the iterates of this dynamical system are, of course, on the base the iterates of the torus translation, while on the fiber we have a product of matrices that are obtained by sampling the fiber dynamics along the fiber along the orbit of the base dynamics. So given, sorry, I think I'm not able to use this. So given such a dynamical system, we define the Lyapunov exponent as the almost everywhere limit of these geometric averages of the norms or maximal expansions of the fiber iterates, right? So this is the Lyapunov exponent of the system. Note that it is greater than is non-negative because we consider SLM matrices. Okay, obviously the Lyapunov exponent depends on the data, and the data in this case it's the base dynamics, the frequency vector, and the fiber map A. So the question that motivated the projects that I'm about to describe was posed to us by Jiangong Yo and concerns the stability of this quantity under random perturbations of the data. Evidently, the Lyapunov exponent is an asymptotic quantity. Its computation, when done by approximation, incurs errors. These errors have to do, in general, with the lack of accuracy in measuring the input data, right? And we can interpret this lack of accuracy in the input data as a kind of random noise. And then the natural question is, well, do these errors have a significant impact on the computation of the Lyapunov exponent or not? So the question of stability under random perturbations of the data, right? Of course, this question makes sense in a much more general setting, not just for cocycles over a torus translation. You can consider any ergodic base dynamics, a linear cocycle over it, the Lyapunov exponent, and ask the same thing. If you perturb the system, do you have stability of the Lyapunov exponent? I'm not going to talk about this primarily because we have not worked on this more general question, but also this original question of Yo was in this setting, and in fact, it was in a more particular setting. It was for cocycles, linear cocycles that are associated to some objects in mathematical physics called Schrödinger operators. I'm not going to talk about this, but this is the original question. It has relevance in mathematical physics. Let me leave it at that. So, okay, the question is, what does it mean to randomly perturb the input data? And so I'm going to describe what we can do. Well, first we can add noise to the base dynamics. So the base dynamics is theta goes to theta plus alpha, right? So you have given a sequence of IID random variables on the torus and a small epsilon. When we rotate or translate by alpha, right, we can make an error. This is where we can get some small random noise, right? So this is the lack of accuracy. When we do this again, we perform another translation with another loss of accuracy, and so on, right? So denoting these random variables by alpha 0, alpha 1, alpha 0, alpha 1, and so on. Instead of this original deterministic dynamical system, the torus translation, we end up with a stochastic dynamical system, which is simply, so the stochastic dynamical system, it's a random translation on the torus, right? So this is one thing that we can do. This is one way to introduce randomness into the random noise into the system. Another way is to add noise to the fiber, right? To the fiber dynamics. So add noise to the fiber, which is the map theta goes to A of theta. Right? So normally the iterates of the fiber dynamics are we sample this matrix A along the orbit of the torus translation. But if we have some noise, then instead of sampling always this same map A, we are going to sample some maps that are chosen randomly according to some distribution. And these maps are going to be, well, to be a small perturbation, they will have to be close to the original map, right? So how can we model this? Well, consider, again, a sequence of random variables, IID, random variables on some space that I'm going to define, and then a function now to introduce the randomness that take this into account, right, the space of symbols, and then the matrices that I'm going to, these random matrices that I'm going to consider are A sampled at the 0th random variable, and then A at omega 1, the next random variable, theta plus alpha, and so on, A of omega n minus 1, theta plus n minus 1 alpha, right? So this is a way to introduce randomness on the fiber. And it should be, well, we are talking now about small perturbations, small random perturbations. So this A of omega 0 theta should be a small perturbation of A of theta. So how can you do this? Well, you either add a little bit or multiply by something that is close to the identity. So, so we do the latter. We consider this. So then this space of symbols is the Lie algebra of SLM-R. Okay, matrices with trace 0 that lead to determinant 1 for the exponential. So this would be the way to interpret this this question, and of course we can do both. Right? We can add randomness, noise on both the base and the fiber. Well, it turns out that all of these, to model these randomly perturbed quasi-periodic cocycles, we would have to consider linear cocycles over a different, more complex base dynamics than the original torus translation. And this is what we call mixed random quasi-periodic base dynamics. So what is this? We start with the Bernoulli shift over a space of symbols. This space of symbols could be the torus. If it's not, we take a map that sends the space of symbols to the torus, and then we consider the skew product map that on the base is just the Bernoulli shift, and on the fiber we translate by right, random frequency. Okay, so this would be basically the way to model this stochastic dynamical system that I described there as a deterministic dynamical system. Right, so we call this a mixed random quasi-periodic base dynamics. We wrote a paper that appeared recently in the Brazilian bulletin of the Brazilian Mathematical Society, where we studied, amongst other things, the ergodicity of this map. We also are about to finish a preprint where we study the statistical properties of this map. In any case, in the special situation in which this function from the space of symbols to the torus, it's constant, then this map becomes just a direct product between the shift and the torus translation, right? This would be the situation where we only add noise to the fiber and we leave the base deterministic, right? So this is in itself interesting also. Okay, so this is the base dynamics, and now let's define the fiber is just a function defined on the phase space with values in the group of matrices that depends. Okay, you have two coordinates. You have the random one right? And then you have the quasi-periodic. Omega is a sequence, and theta is an element of the torus. So this function, well, on the quasi-periodic variable a priori is continuous. In the other is locally constant, depends only on the zeroth coordinate or on a finite number of coordinates, right? Like in the case of random cocycles, linear cocycles. So this is the type of linear cocycles cocycle that we consider, that we call mixed random quasi-periodic. This is how the iterates of this system look like, and just like linear cocycles over a locally constant cocycles over a Bernoulli shift encode products of random matrices. This would encode compositions of random quasi-periodic cocycles, right? Okay, so now we want to talk about small perturbations, right? This is just a model that it's using the terminology although it's a different thing that Luna used. This is a mating. This is a mating between quasi-periodic and random cocycles, right? If you want. And then, so let's consider one in which the noise, the random part, is small, right? So the fiber map will be given the way I described earlier as a small perturbation, right, of the quasi-periodic part. Okay, so then we can now formalize the question posed by Zhang Gongyo in the following way. What happens with the Lyapunov exponent of this cocycle, right, over this more complex base dynamics as the noise, as epsilon goes to 0? In other words, is the Lyapunov exponent as a size of the amount of randomness continuous as epsilon goes to 0 at the point 0, right? That's the question that we wanted to answer, and which would establish, if true, the stability of the Lyapunov exponent, and also justify this sort of computations that are done by approximation. Well, so before we let epsilon go to 0, actually we realized that we didn't know anything about the system, this mated system between, right, the mixed random quasi-periodic. We knew a lot about the quasi-periodic setting. We know a lot about the random, right, the cocycles over the Bernoulli shift, but not about the mixed model. And so let's talk about this. Forget about epsilon. Fix the amount of randomness, right? It doesn't go to 0. And let's see what is natural to ask about this model and what we managed to show. So again, our dynamical system is this Q product. Here we have on the space, we have the shift, we have a random translation, and we have a linear map induced by this matrix valued function. And then we can talk about the Lyapunov exponent of the system, and there are some natural questions that one begins to ask about the Lyapunov exponent of really any system. Namely, when is it positive or simple, right? Have some criteria that ensure the positivity and the simplicity of the Lyapunov exponents. When is this map continuous, right? The map that assigns to the data, whatever that is, the Lyapunov exponent itself, and whether this continuity is not merely qualitative, but is also quantitative, whether there is a modulus of continuity like Hölder, which is the best that can be in general. So it needs to be said, so I'll say it, that the question of continuity of Lyapunov exponents is in general a very delicate matter. And let me illustrate this with a few examples of results in the quasi-periodic setting that explain this point. Why is it delicate? So consider, so now I'm in the case where the base dynamics is the torus translation, right? It's not mixed. It's an older topic. So it's the torus translation and the map that defines the fiber. Depending on the properties of the frequency vector and the regularity of the fiber map, we may or may have continuity of the Lyapunov exponent. So there is a series of results that start with the work of Bourgain, Zhitomirskaya, Gorsin, and Schlag, Marx, Avila, Zhitomirskaya, Sadel, and eventually Pedro and I, where we consider analytic. So we assume that the map that defines the fiber dynamics depends analytically on the point, and we assume that the frequency vector satisfies some reasonable arithmetic assumption. Then the Lyapunov exponent is a continuous function, in fact, Hölder continuous, on the data, which is the fiber map. If, on the other hand, the regularity of the fiber map is lower, it's smooth, even with the best possible frequency that you can consider, one of bounded type, for instance, the golden mean, even then, there are points of discontinuity, which was proven by Wang and the same Jiang and Guo. Now, moreover, recently, Avila, Last, Shamis, and Zhou showed that even in the analytic setting, if you take away the good arithmetic properties of the frequency, so you take something very Liouvillean, then, okay, the Lyapunov exponent will be continuous. This is the work of Bourgain, Zhitomirskaya, and others. But the modulus of continuity could be arbitrarily weak, right? And this is not the end of the story. Of course, there is space between analytic and smooth. And there is a certain class of functions called Gevry functions where you have a sort of threshold of regularity. Okay, so this is the quasi-periodic setting. Now, in the purely random setting, what does it mean, purely random? You have a linear cocycle over a Bernoulli shift, and the fiber dynamics is locally constant, so depends on one coordinate or a finitely many. So this is the best regularity possible. In this setting, things are much better. They are delicate, but they are more certain. When the map, the fiber map is more general, I believe that Karina Marin will talk about this model, things can get much more, can get again delicate and less certain. But here we understand much better what happens. So firstly, by Furstenberg's criterion, generically the maximum Lyapunov exponent is positive. And in this generic setting of Furstenberg, the Lyapunov exponent is continuous by work of Furstenberg, Kiefer, Lepage, Pedro, and I. And without this genericity condition, more recently, Boker and Marcelo Viana, Avila, Eskin, and Viana, and Pedro and I forgot to mention Toll and Marcelo Viana proved continuity with some modulus of continuity of this object, right? So these are the two, the quasi-periodic and the random, what happens with them, and then the question is for the mixed model. And then the last question is to let the randomness go to 0, right? Okay, so then the question is, given what we know about the quasi-periodic model and the random one, what we should be expecting about the mixed one? And it took us a while to realize this, but the expectation, and first you need to believe it, then you have to try to prove. So the expectation is that if the random component, so you look at this model, if the random component is non-trivial, then it should be dominant over the quasi-periodic one. In other words, the model should behave as if it were a purely random, right? What does it mean that this random component is non-trivial? Well, if you have either the base is stochastic, right? You have some noise there, or if it's not, if it's deterministic, then at least you have some noise on the fiber, right? Which is non-trivial in the sense that the probability distribution that drives it is not trivial, is not supported, is not a Dirac delta, right? So if that's the case, then the system should be more like the random one. And this was actually shown by a result in this direction was obtained by Jamerson Bezerra and Mauricio Poletti last year. They proved that generically we have positivity and continuity of the Lyapunov exponent of quasi-periodic, of mixed random quasi-periodic cocycles in a certain setting, which is when the measure that drives this randomness is finitely supported. Right? I believe that this was part of the PhD thesis of Jamerson under Marcelo Viana. So we extended, well, using also different methods this year, this result. In fact, what we did, we created an analog of various results of Furstenberg's theory for non-commuting random products for compositions of random quasi-periodic cocycles. So in particular, we obtained a criterion for the positivity of the maximum Lyapunov exponent that resembles the Furstenberg's criterion and which is generic. And moreover, we showed that the Lyapunov exponent is continuous in this open set of cocycles. I want to make a comment about this result. One other reason that we think it's interesting is the following. As I mentioned before, if you look at quasi-periodic cocycles, right, purely quasi-periodic, all kinds of things can happen. So if, for instance, you start with the fiber dynamics that is not sufficiently regular, or if the translation vector is not too, it's Liouvillean, then these results may fail. Once you add a bit of randomness into the system, all the problems are solved. So you get the continuity, you get the positivity of the Lyapunov exponent. So this randomness has a regularizing effect, as perhaps expected, right, in general, on the Lyapunov exponents. Okay, so this is one result. I should say that results in the spirit of the positivity result, or in other words, of the.
What do you mean by non-compact?
Well, this would be well, the norms increase, yes, in this sense, yes, under iterations, yes.
Not contain retreads on
Yes, the support would not be in a compact, yes. So results in the spirit, but for the first part, not the continuity, for the positivity of the Lyapunov exponent. So the analogs of Furstenberg's result were also obtained by Kiefer, Fuhrman, Monod, and more recently by Goldschmidt, and separately by Gorodetsky and Klepsin. In fact, they obtained, Gorodetsky and Klepsin, a version of a non-stationary version of Furstenberg's criterion for the positivity of the Lyapunov exponent, which would be more general than our result, which is more specific to randomness over a quasi-periodic environment. Okay, well, so the next question is, what about stronger continuity properties of the Lyapunov exponent, for instance, the Hölder continuity? And well, to answer this question, and in fact, in our case, to prove any kind of continuity, we use an abstract result that Pedro and I proved in a while ago that says the following, that if in your space of cocycles you have a certain type of statistical property that we call uniform large deviation type estimate available, then automatically the Lyapunov exponents will depend continuously on the data with the modulus of continuity that depends on these statistical properties. In general, it's Hölder, right? So let me describe this, this type of statistical property, uniform large deviations estimates. So this applies to any type of linear cocycle. Suppose we have a linear cocycle over any ergodic-based dynamics. By the ergodic theorem, these geometric averages converge almost surely to the Lyapunov exponent, right? So in particular, this tail event converges, right? The measure of this tail event goes to 0. When there is an effective rate of convergence to 0 of the measure of this tail events, then we say that the system satisfies a large deviation estimate, right? This is a kind of, this is related to the large deviation principle of Cramer in classical probabilities, except that it's a finitary statement, it's not asymptotic. Okay, so in general, this rate of decay to 0 we managed to show that is exponential. So when this happens, now, this rate of decay, there are several parameters here. You have to iterate the system long enough to guarantee that this happens. Then there is the rate of decay here. So there are certain parameters that describe this statement. When these parameters don't blow up as we perturb the cocycle, we say that this estimate is uniform, right? So then the result says that if we have this in our space of cocycles, then automatically we have continuity with the modulus of continuity. If this rate of decay iota was exponential, then which is the best that it could be, typically then the modulus of continuity would be Hölder, which is typically the best that it could be. Okay, so then the goal is to this turns the question of continuity of Lyapunov exponents into a different kind of question, which is interesting in itself, proving statistical properties for these dynamical systems. Well, specific statistical properties, large deviation type estimates, but in the same way, one could also get central limit theorems and other such results, right? So then the question becomes proving such statistical properties for mixed random quasi-periodic systems, right? So here is a result which is not yet available, but it will be soon, where we assume the following. We consider this case in which the base dynamic is deterministic. So we don't put noise there, we put noise on the fiber. And then if we have noise on the fiber, assuming that the maximum Lyapunov exponent is simple, is different from the next, and assuming that the cocycle is irreducible, which is a generic condition, right? Then we have these kinds of large deviation type estimates, and that are exponential, and in particular, the Lyapunov exponent will depend continuously, Hölder continuously on the cocycle, right? So this is the statement. This again is when the amount of noise is fixed, right? This is for that model. Let me just say one thing about this. How do we in general prove these kinds of results? Well, I actually forgot to say that the odd object in all this story is the purely quasi-periodic model. There, the approach is analytic. We use harmonic analysis, we use potential theory, subharmonic functions, and so on. All the other models are treated along with the study of statistical properties of other types of dynamical systems, not just linear cocycles, using a functional approach. which looks at the spectrum of a certain operator, the transfer operator or the Markov operator, and on an appropriate space of observables, one proves that the existence of a spectral gap. So the fact that the spectrum consists of a point of modulus 1 and the rest of the spectrum is contained within a disk of radius strictly less than 1, right? So this is the spectral type property that is then used to establish these statistical properties for various types of dynamical systems. In this case, for this model, it happens that the spectrum of the transition operator that we consider on an appropriate space of observables consists of something that is inside the disk of radius strictly less than 1 and the entire circle of radius 1, not just a point. So in some sense, we have a spectral gap, right? It's, the spectrum is separated. But it's not a spectral gap in the sense that it's normally expected or used. So we have to deal with this situation. We had to create a new technology that actually was, we were able to use it and simplify other arguments for models that were previously studied. So, but anyway, this is the case when the amount of noise is fixed. So now let's allow the randomness to go to 0, right? And see what happens. And so this is the result that we get. So firstly, here we do not need much about the system because the randomness is enough to regularize everything, right? So in particular the fiber dynamics has very mild regularity in theta. The frequency vector doesn't have to satisfy any arithmetic condition properties. So just the fact that there is randomness, there is some noise, this is enough to regularize and obtain the statistical properties. On the other hand, when we allow the noise to go to 0, we have to begin with in our best possible shape. So we assume that the data is the best the initial data, the non-perturbed data is the best that can be, right? So it's the fiber dynamics is analytic, right? The unperturbed, the epsilon equals 0, the frequency vector, the translation satisfies some generic arithmetic condition, right? It's not very rational. No, it's very irrational. So this is what we assume on the unperturbed system, right? And then we introduce the noise. So the assumption that we make on the noise is given by some random variables that are that correspond to a probability distribution that we assume to be strong enough. So in other words, we add a spreading condition on the product measure mu. It's a technical condition I prefer not to describe here. It's a general but relatively technical condition that that can be greatly simplified as positivity of the Hausdorff dimension of the measure in some particular situations, right? So under these conditions, the map that assigns to the data, which is the fiber map and the amount of noise, the Lyapunov exponent, is Hölder continuous in a weaker sense, including at 0. In other words, we have this stability of the Lyapunov exponent under random perturbations, and we have a stability that is in some way stronger, right? There is a modulus of continuity there, right? What does it mean, what? it's a modulus of continuity that is a bit less than Hölder. But yeah, I guess I can write the formula. I cannot write the formula, but it's a bit less than Hölder. So Hölder would be what? H to alpha, right? Which is e to log 1 over h alpha, right? This is the, so then if you put a power here that is less than 1, that's weak Hölder, right? So this is 1/2, for instance. Okay. Okay. So this is the result, and let me just. It was said that every talk should contain a proof. That it's something that I actually used to believe in, and so I think I have a few minutes to not to prove this, but to give a very rough idea. So actually, what we are doing, we are combining two very different objects, right? The limiting object, the quasi-periodic one, satisfies. So the goal again is to prove this large deviation type estimate in a uniform way with respect to the noise epsilon, right? That's the goal. And so on one hand, the unperturbed system satisfies these properties, right? The statistical properties. So we have a large deviation. Let me just put the large deviation. It's here. So this is satisfied. But it's the way we get this estimate is through a process that that depends on subharmonic functions estimates. It's purely analytic, right? And there are some parameters that determine this estimate. On the other hand, when you perturb the system, right, we also have these kinds of large deviation estimates with some parameters that a priori depend on the number of on the strength of the randomness of the noise, depend on epsilon, right? For instance, to get this kind of estimate, you would have to iterate the system long enough until you see this happening, until you see this behaviors happening. So then we have these two. I think I have to erase this, right, for the camera to catch. So when we have noise, when epsilon is positive, we have these large deviations estimates for the perturbed system, a epsilon, after a certain number of iterates of the system that clearly has to depend on the amount of noise, on epsilon, right? So you have this threshold. Now, when epsilon is 0, we have a quasi-periodic cycle, the best that it can be, so we also have large deviations, for instance, with possibly different parameters, right? Now, by proximity, we know that the unperturbed system differs from the perturbed by something of order epsilon. So if we perform n iterates of both systems, perturbed and unperturbed, then the difference between these averages will be of order epsilon and a constant, an exponential, right, of n, a constant that depends on the cocycle. And we want this to be very small. So for this to be very small, this number n of iterates should be of order at most log of 1 over epsilon, right? So we have another threshold here, n0, which is of this order, log of 1 over epsilon. And what can we say up to this threshold? That since the unperturbed system satisfies large deviations, the perturbed one, by proximity, will also satisfy. So here we have large deviation by randomness, right? We have some noise, we have enough noise, and here we have large deviation by proximity to the unperturbed system. And we want to have large deviations throughout, right, for all iterates. So the question is, how do these thresholds compare? Well, ideally, the second would be less than or equal to the first one. In an ideal world, we are not in an ideal world by all means, right? So what we managed to do was to estimate this threshold. And it turns out that this threshold is of order not log of 1 over epsilon, but it's some power. Let's put something like this. It's not this, but it's some power of it. So there is a space, but we are able to fill in the space in some way. The hard part is not to fill in the space. The hard part is to relate. So what is it that's happening here? We have to relate the amount of random noise to the number of iterates that we have to perform on the system until we start filling the randomness. Right? So this is what has to be estimated. And this is where we use several things. One is the assumption on the measure, the spreading property of the measure that I did not describe. Another, we have to go back, look at the unperturbed system, and look at the tail events where the large deviations for the unperturbed system do not hold, right? The part of the space that, well, the tail event that has a small probability. But it doesn't just have a small probability, it also has a bounded algebraic complexity. And because in some sense it's a semi-algebraic set because of the regularity of the data. And then doing this together with the spreading property of the measure, we are able to escape this. I got the signal. Okay, so I'll stop there. Thank you.
Okay, thank you, Silvius. Question or comment?
I have two questions. Maybe the first one, what can be said if you don't assume that your noise is finitely supported, but just it is concentrated in the small neighborhood of...
We don't assume this. This was the assumption in Bezeha and Poletti. Okay. We don't assume this.
Okay, so this is close. And do you have any counterexamples, like if you have analytic cycles, and then if your conditions are not satisfied, you don't have continuity?
For the mixed model.
At zero.
At zero. So if it's if it's analytic, it's always continuous. The question is.
No, but if you perturb.
When you add the randomness. This I don't. Okay, the example would have to assume that the randomness is not rich enough. This I don't. This is a good question. That for now we have a positive result. We have a sufficient condition that ensures this. But yes, I don't know. It's something to think about.
Okay, thank you. And well, let's thank again to Silvius, and we please. Next talk is 3 o'clock.